So today is about something really, really cool, really, really fancy. I don't think we'll finish today. Called the Lovász local lemma, and a spectacularly elegant algorithm. Uh, that was actually developed by a grad student like you. So yeah, this is one of those discontinuities in the fabric of knowledge. Okay, um, so we talk about SAT a lot, right? We talk about a lot in undergrad algorithms. We talked about it the very first week. We did that approximation algorithm, 7/8. So SAT comes up again and again. And that's also sort of the motivation here. Um, okay, in general, the challenge is you're given a SAT formula, and the question is it satisfiable, right? But suppose you're looking at a K-SAT uh, algorithm. So every clause has exactly K variables. And I told you the number of clauses was less than 2 to the K, which may still be big, right? Because it's 2 to the K. So what can you tell me about a formula where the number of clauses is less than 2 to the K? Or maybe you can't tell me anything. Yeah. There could be duplicate. Oh, yeah, within a clause? That's right. Okay, why? Oh, okay, that's a direct way. Uh, so the argument was there's 2 to the K combinations. For each clause, only one of those combinations kills it. There's some kind of something's left out kind of argument. Uh, what's like a probabilistic way to express the exact same argument? Yeah, so each of these, okay, so the probability, so let's look at a random assignment. This will actually amount to the exact same thing. Um, Probability that the formula comes out false, right, by the union bound. The clauses aren't independent, they can share variables. It's going to be the sum over all the clauses, the probability that the ith clause is not satisfied. That's 1 over 2 to the k. Oh, because there's nothing written here. M times 1 over 2 to the k, and that'll give you, oops, and that'll be less than 1. So there is a chance that the formula will be satisfied, so there exists a combination that the formula will be satisfied. Right. We're basically same argument. Um, okay. Of course, if m is bigger than 2 to the k, then the union bound is not strong enough, or this sort of something is left out argument is not strong enough. Okay. Of course. So, right. All right, so consider this algorithm, which at some level you might have coded up if you were just trying to come up with something. Okay. So, it's sort of like just building on the previous one. I'll initially sample a random assignment, and then I'll pick up a clause and say, oh, this is not happy. I'll just resample those variables, resample those variables, resample those variables. It's like, okay, maybe this will terminate, this won't. It will terminate if you succeed and you find a satisfying assignment. But it might not terminate, of course, if the formula is not even satisfiable. Okay. So, so that's the algorithm of Moser. Um, and here is an incredible claim. So you should stay for the claim. Okay. Let F be a formula, be a K-SAT formula, and we're going to focus on, for a particular clause, how many other clauses does it intersect? This is where the word local from local lemma is going to come in. So each clause, we're looking at a special case where each clause maybe shares a variable with only 10 other clauses or something. Okay, so then if D is at most 2 to the k-ish. 2 to the k over e minus 1. Okay. Then, who wants to guess what comes next? Yeah. F is satisfiable. Okay. And the algorithm will terminate, and if you look at it closely, it's going to resample each clause, I guess 1 over d times, which is less than 1 in expectation. Yeah, clauses can have negations. They intersect if x1 is here and x1 bar is here, they're intersecting. Just sharing underlying variables, not literals. Yeah. Okay. So it says there's some limited dependency of one clause on the next. Okay. So it's not fully independent, but there's some limited independency. Then it will succeed. Okay. Obviously, if it was fully independent, if d was 0, this is very easy because they're not sharing any variables, or in general, there's some chance. But it's saying if the dependency is somehow 2 to the k over e 2 to the k is how much randomness is going in each side in each clause, right? So if kind of locally, if sort of your dependencies are, and you can sort of see some intuition, right? Okay, I have a clause that's not satisfied, so I'm going to resample it. It'll probably get that clause correct if there's 10 variables or something, right? But it's going to mess up some other clauses nearby, so you have this like epidemic of mistakes. But you're trying to argue that at some level, 2 to the k over e is almost like being able to take a union bound over all the neighboring clauses. Not quite, but almost. Okay. And it's almost saying like, if you can kind of take a union bound over each sort of neighborhood of clauses, then something like our initial argument, m is less than 2 to the k or something, kind of seems to hold. Okay? They're just trying to build some that's not very formal. I'm just trying to build intuition for what is sort of a spectacular claim. Yeah. You can do whatever you want. Yeah, so you can sample that clause if you get unlucky. You can sample that one again, or you can choose some other one that's not satisfied. Yeah. Yeah, so it seems like if first of all, there's a chance that I just miswrote something. But if I did not miswrite something, then it looks like it's going to be less than 1 per average, right? But then you spread that over all the clauses, and you're going to resample a total of m over d clauses. Because there's m clauses out there. But each one on average, each one will be 1 over d, and then a more meaningful bound comes from adding them all up over all the clauses. Yeah. So you won't resample very much either. The algorithm's kind of fast. Okay. So, so that's what we're going to prove. I don't think we'll finish it today. It'll be by far the most complicated thing we've done so far. Okay, so I want to make some points. So the conditions intersecting at most d other clauses and d less than equal to 2 to the k over e minus 1, these are like locally verifiable, right? Just look at a clause and see how many neighbors there are and check to see if it's big. So if this theorem was true, then okay, this algorithm will find a satisfying assignment. What's a simpler algorithm to tell me if f is satisfiable? Well, I can just calculate d and compare it to 2 to the k over e minus 1 and just answer yes or no, right? Which at least will work in one direction, right? So it's locally verifiable. It's a local condition. That's why it's going to be called the local lemma. Now, the algorithm is more new. Okay, so the algorithmic aspect of it is from 2009, okay, which is not that long ago. Well, actually, for you, it was a long time ago. But compared to other things we've done in this class, this is relatively recent. I don't know what happened in 2009 that was interesting. It was a landmark event in 2009. When does Twitter start? Earlier? Instagram maybe? I don't know. Okay. Uh, the claim that F is satisfiable, this actually goes back to the 1970s. So this is a big theorem from kind of discrete math, randomized math, probabilistic method, combinatorics. Okay, so this can also be applied to things like graph coloring and stuff. I think you'll get an example in homework. Okay, and there in Math World, they actually had modeled this more abstractly. So this is the more abstract version of it. So the idea is that you have some events, right? So you have these events you want to avoid, A1 through AN. I probably should have done AM, because an event could be like the ith clause is not satisfied. So I want all the clauses to be satisfied, so I want to avoid any of this. This clause is not satisfied, that clause is not satisfied. Those are different events. Okay? And the local lemma is going to focus on the events that are not independent. Okay? So they're almost like nodes in a graph. Each node is an event, and some are dependent on each other and others aren't. Okay? This can be weakened slightly to like negative correlation, but that's okay. So the question is it possible for none of the events to occur simultaneously? So again, if each event corresponds to a different clause being not satisfied, is it possible to have no clauses unsatisfied? That is it possible to have all clauses satisfied? And well, there's two kind of obvious answers. One is, if they're independent, then the answer is always yes, it's possible, right? Because they're independent of each other. Probability might be very, very low. Okay, but it's possible. I mean, assuming each one individually has a non-zero probability of not occurring. On the other hand, without any assumptions, the answer is no. Right? Maybe one event is this coin comes up heads, and the other event is the same coin comes up tails. Then they're just going to be the XOR, I mean, the opposite of each other. So you'll never get this to happen, right? So you need some assumptions on the dependency. And there even, that's just one dependent event, but somehow one coin is not enough randomness, right? So there also needs to be some understanding of the dependency among the events relative to the amount of randomness at play. Okay, and good. So okay, so here's the abstract version. And it's a little bit, I guess abstract's the right word. Suppose I'm somehow able to assign values to each of the events. Okay, we'll parse this slowly, such that for each I, the probability of event I happening is at most xai, this value assigned to ai, times the complement value, 1 minus x aj over all events aj that depend on ai, excluding ai. Okay. Then there's a non-zero chance of this happening. None of them happen. Okay, so this is a very bizarre statement. Okay, and this might seem quite abstract and like, why would you formulate this way? But then there's other problems. We'll probably focus on SAT as our working example, but like, weird sort of coloring bounded degree graphs, list coloring bounded degree graphs and hypergraphs. And there's a lot of different situations in combinatorics, these extremal situations that they're interested in. And if you just find some clever way of plugging in X, you get some crazy graph theorem or something. Okay. So, or maybe to make it a little more concrete, here's one corollary. So this one will look a little bit more like SAT. Suppose each AI is independent from all but D other events AJ. Okay. and all of them have the probability of happening bounded by some probability p. So this is some kind of uniform setup. Okay. Then, if e times p times d plus 1 is at most 1, then the probability of them all not happening is greater than 0. Okay. And so to prove this, given the more abstract version, you set x to be 1 over d plus 1, you just plug it in. Okay. I mean, probably this one was, the simpler one was discovered first, and then they looked at some non-uniform settings that they wanted to prove, and they said, oh, I can adjust this, I can adjust that, and then out came out the more abstract version. Yeah. Okay. So, I just want to let you guys know that this exists. In our discussion, maybe I'll focus most, or at least I'll talk as if we're focusing on SAT just to keep things concrete, intuitive. But it's good to know that these ideas exist in much more abstract setting. So, what's the point of this slide? Okay. So that's the classical results. They cover the part where f is satisfiable, but they don't say much about any algorithm. And you could ask, okay, do we have algorithms for the more abstract setting besides SAT? And we do. So, okay, so to come up with some kind of algorithm, we need some notion of resampling an event, right? Because before I just said, oh, there's events and there's no underlying, what drives these events. So we'll take a slightly more like mechanical model, so slightly restrictive, but I think in all applications you can come up with this. We're going to assume there's some kind of underlying variables, okay, which, for example, in SAT would be setting x1 to be true or false. Okay. And we're going to assume that each variable xi is independent with its own distribution. So there's some underlying sort of generating bits in some sense. Okay. And each event AI is determined by a subset of these variables. Okay, so the original framework with all these events is very abstract. Now we're going to assume there's some underlying set of random variables that are all independent. Each event AI is determined by a subset, and then we'll do our dependencies accordingly. So I'll say AI and AJ are kind of connected if they share at least one of these variables. Okay, so with SAT, the events were clauses, and the underlying variables is a coin flip for each variable. Is it true or false? Is it true or false? Is it true or false? Those are independent, and then two clauses are overlapping only if they share a coin, which means they share a variable. So, good. That is, so that's how we at least get something set up, right? Now you can at least work with something algorithmically. And so the more general version of the algorithm in this notation is first you just sample all the underlying variables. For SAT, you flip all the coins. Okay. And then while there's an event AI that occurred, something you don't want to occur, you're going to resample the underlying variables from their respective distributions. So for today, it's completely fine to just assume the events are unsatisfied clauses and the variables are the underlying Boolean variables of the clause. Although I think notationally I'm going to present it in a more abstract thing. And then you can look back and be like, oh, okay, so it always held more abstractly, even though it was nice to think about clauses. Yeah. AI tilde AJ means it's not independent. They share variables. Yeah. I don't know what the best notation was, so I just used tilde. I kind of think of it as like an edge in a graph. Yeah. So they're kind of similar. Yeah. Yes. Yes. So first there's cases where there's more than two choices, like in graph coloring, you're choosing one of k colors. And then yeah, so the quick answer is yes. I'm struggling a little bit to think of a concrete example. So mm, yeah, the answer is yes, but I don't have an example at the top of my head. Um, I once worked through. There's a very nice book on graph coloring by these combinatorialists in Canada. Um, and you can take this and make it much more sophisticated uh, as well for what it's worth. There's actually also kind of algorithms that go slightly beyond this and arguments that go slightly beyond this. Like some will kind of like, say you're doing graph coloring, instead of just looking at the neighboring vertices, it'll look at like two hops away and do some more elaborate argument based on that. I'm only speaking a little abstractly because I haven't thought about it in a few years. Um, and I forgot. Uh, yeah, there's just some impression made on me. Yeah. Well, yeah, probably in real life, you'll choose a natural distribution based on the problem. The theorem just says you're given a distribution for which this holds. And the algorithm is just going to say, oh, you have some distribution of the underlying variables for which the conditions hold, and I'll just sample from that distribution. But probably you're going to be given a real world problem and want to come up with a distribution yourself for that problem. So for SAT, I think flipping everything heads or tails with equal probability is a reasonable choice. You may find situations where um, some weird situation where you notice a variable only occurs positively once and negatively a lot. So maybe you want to bias the coin towards the negative side, and you can do something that goes slightly beyond the worst case bounds given here. But that's not. Well, I don't know if that leads to natural clean characterizations that are worth making a big deal about. But yeah, you might be able to come up with better distributions on a case by case basis as well. Yeah. Okay. So good. Um, so this resampling algorithm, again, if it satisfies the same conditions as before, um, then it's going to find some configuration eventually. And for each event AI, the number of times it's going to be sampled in expectation is this quantity xi divided by 1 minus xai. That corresponds to 1 over d or something from before. Okay, so that'll come up in our proof. For now, it's just something. So this is probably less than 1 for a small value of x. Yeah. The algorithm doesn't actually need the values x. So it's just an existence of x, which means, yeah, so that just means there exists some running time at some level. Yeah, I guess so. So I guess the running time of this algorithm will ultimately depend on the best of all possible ways to choose x, even if there's a secretly one that's better than the one you came up with. Yeah, it doesn't affect the algorithm, but it does affect the running time. But this is sort of like basically not having a very good closed form solution. X is going to satisfy something that shows up in the proof. Yeah, if there is some X's, and then the proof goes through. And in many of the other things we had, we also said like, oh, okay, if you have some values, this will work. What's the best value? Oh, by AMGM, it's this or something, right? And that had a cleaner thing. Of course, sometimes we misuse AMGM, but but in many cases that the setting was simpler and we can actually just pinpoint, what would be the exact X's or something to make something happy. And I guess here it's just getting a little complicated, so we don't have as clean of a theorem statement. Yeah. This is definitely a little bit more mysterious than and less direct. I think you agree by the end of this lecture or next than some of the things we've done up to this point. Yeah. Huh? Yeah, so you're assuming you're in some algorithm that can observe the events and whether they happen. Like if it was sat, you can just check to see if the clauses are satisfied. And uh, yeah, so this seems abstract, but it basically covers a lot of concrete cases like graph coloring and things like this. But yeah, you can loop over. You can say for I equals 1 to n, if one of them is a present, resample it. And if you get from 1 to n, you don't find any of them occurred, then you're done. So yeah, so you can while there is an event AI, that could be a loop checking all the events. Or you might potentially do something smarter, right? Like if you're doing sat, you know that if you resample a clause, you only have to check the neighboring, you know, clauses and stuff like this, right? So these algorithms are ridiculous. Take sat for the sake of concreteness. You might be really close to satisfying a formula. You only have one clause left. You resample it, and now you make mistakes elsewhere, and you go backwards. These are not algorithms that are always making forward progress in any obvious way. Okay. Exactly. So if I give you a sat formula that can't be satisfied, then this algorithm will never terminate. That means there couldn't exist x's to make this possible as well. So this algorithm is only running in a situation known since the 1970s to have a satisfying, happy outcome where it's possible. And the real breakthrough in 2009 was to come up with an algorithm for it. Right? This was like one of these huge, outstanding problems of there's something the mathematicians figured out and the computer scientists haven't caught up yet. And that gap was there for like 40 years or 35. So that was a huge breakthrough when this was solved in 2009. And amazingly, it was done by a graduate student. Yeah. So not to put pressure on you guys. Um, yeah. So, uh, but yeah, this was sort of, result of the year when it occurred. The algorithm itself, it's possible that some people were trying out this algorithm heuristically anyway. It's very natural. Okay. Okay. So the proof is crazy. So we're trying to argue. So the notation will be in this abstract event framework, but I will just talk about clauses and variables because maybe that's easier to think about concretely. Okay. So so as we have already observed, it's not clear why the algorithm works. Clearly, the algorithm is not necessarily making monotonic progress. It's not always satisfying more and more clauses or anything like this. So you have to do something a little different. So Moser's original proof was something based on an entropy compression argument. There's a nice blog post by Terence Tao about it. And in the journal version, he he teamed up with Tardosh, who's actually the brother of the Kleinberg Tardosh from the textbook. Um, and then this proof here is coming from the Moser Tardosh journal version following up. Okay. And so, okay, we're going to introduce two uh, interesting objects, which were, I think, in Moser's original proof. One is this idea of a log. So as the algorithm does stuff, oh, I sampled event 1, event 2, or clause 1, clause 5, clause 7, you can write that down in a log. And somehow we're going to transform those logs into a certain kind of tree, like structure called a witness tree. And then it'll be an eccentric argument. So, um, yeah, and I think it was an argument that was very novel at the time. So, okay, so first, object is this log. And what we're going to do is we're going to record all the events that we sample in chronological order. So maybe you first say, oh, event 1 occurred. I don't want that to happen. I write down A1. Then I notice that event 7 occurred. I don't want to happen. So I sample A7. Then I sample A11. Then I realize event 1 has occurred again. I sample A1. Okay, so that's just a log. I'm just going to write things down. Oops. Yeah, sorry, I had this yeah, just the events. We're not going to record the values. Yeah, in fact, that's sort of important. And at some level, to show the algorithm terminates, that means the log ends, right? So at a high level, we want to bound the expected length of the log. Good. Good. Now we have a more eccentric object. So these are called witness trees. And what witness trees are going to be is, at some level, we're going to take these events and we're going to arrange them in a tree-like structure. And the rules are coming up next. But at some level, what we're going to do is we're going to sort of look at a particular prefix of the log, like the first 10 events, and look at that 10th event, and sort of try to reverse engineer, like, how did I get to this point? And we'll kind of put that 10th event at the root, and we'll go to the 9th one and say, okay, is the 9th one related to this one? If so, I'm going to make it a child. Okay, so what are the rules? Okay, so for every prefix of the log, I'm going to generate one of these trees by the following procedure. So let's say the first events are AI1, AI2, up to AII. Don't ask me why I use AII and I use I twice. I don't know. But it's in so many of the future slides, I couldn't change it in the time constraints. Okay? So, okay, but we're going to look at the first I events. And the first step is I'm going to make a root with label AII. Okay. And now for each of the events going backwards in reverse chronological order. So I'm going to look at, say I started with the 10th event. I'm going to look at the 9th event and say, it doesn't depend on any other nodes in the tree, which in particular would say, is there any relationship with A10? Okay. And if it is, then I'm going to put it in the tree. If it's not, I won't. So if it is, then I'm going to find the deepest node in the tree with some relationship to it. Okay. And I'm going to make it a child with that label. So it's like really weird. I start with a 10th event and I make that the root. And then for each event, if there's some connection to some event in the tree, I'm going to add it to the tree, but as deep as possible. Okay. So somehow for every prefix of the log, I'm going to map it to a witness tree. Okay. And nothing down here. Okay, so I guess I set this up as an example because it's such a bizarre construction. Okay, so we're going to try building a witness tree over this log of 6 events. So that's 1, 2, 3, 4, 5, 6. Okay, so that means this is the last event. So this is where the procedure starts. So this goes as the root. This goes as the root. Okay. So the next one is this one. Where does this go? Okay, so there is some connection, so it just goes underneath. Like that. Okay. So, okay, here the events are, these are the clauses of a formula. All right, where does this one go? Sorry? Child of the root? Right, so it's not connected to the other one. That goes here. I hope there's no third child. Okay. How about this one? Okay, so 789, that's not anywhere else in our tree, so we just ignore it. So not all events end up in the tree. Okay. And how about this one? Child of the left child. Like that. And then finally, what about this one? Like that. Okay, so that's how these witness trees are formed. So they'll tend to try to be long because you're always looking for the bottommost child that you can attach it and still have some connection. Yeah. 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 So we are going to, for every prefix, so first of all, this is all in the analysis. The algorithm, of course, doesn't do this. But in the analysis, we are going to look at the trees of every prefix. So for 10, a log of length 10, that's 10 different trees. Not only that, but the trees are going to look completely different because it's the last event that determines the root. So the roots are going to be completely different. That leads to kind of a different construction and chain of events altogether. Um, Although there'll be some, yeah. Well, so for example, you have to figure out how you're going to do tiebreakers and stuff. So I would be careful about the word equivalent. And it's also quite possible that there's only a couple properties we need to extract from this process, and there's other ways to satisfy it. And this is just one way to go about it and to be concrete and specific so that we're all on the same page. Yeah. By the way, this whole proof, I'm very happy if we can come up with a better understanding or anything, because it's kind of crazy. I think the proof I'm presenting is pretty faithful to the original paper, but okay, good. So um, an observation for later, okay, but the main property that we kind of need from these witness trees, you'll see. So let's say that I'm looking at the first L events, and I have two indices j less than k, and they depend on each other. How do they relate to each other in the tree, in particular their depths in the tree? Yeah, j will always be at a deeper level. Um, yeah. So assuming that k is actually in the tree, so it's possible that k didn't get in the tree because there's no dependencies, and later j finds a dependency. But assuming k is in the tree, then the aij is also going to be in the tree because at the very least it's dependent with k, and the depth will be greater because it'll either be k's child or someone else's. Somehow these are probably the main properties that will show up in the proof, probably on Wednesday. Okay. So, okay. All right. Okay, so with all those crazy objects being constructed, our goal is to bound the number of times event AI is resampled, or clause I is resampled. Okay, and okay, so how are we going to argue at a high level? So I'm going to let big W sub I denote all the witness trees with root AI or root clause I. Okay, so there's many possible witness trees that can be constructed, but only some of them have this event as a root. Okay, and given the log, I'll say the log over just the first event, I'll call that T1. The log over the first two events, I'll call that T2. The log over first 10 events, I'll call that T10. Okay. Now to try to bound, So if I want to bound the expected number of times that AI is resampled, so every time AI is resampled, it appears in the log, and that means its witness tree appears somewhere, right? So that'll be the expected number of times that AI appears in the log. And that's summing over all the possible steps. What is the probability that the first tree is equal to some witness tree with root AI? What was the probability that the second witness tree is equal to some witness tree something? Okay, it feels a little analytical. Okay, but nothing too complicated. Now, okay. All right, so did I miss this earlier? Okay, let me go back for a quick moment. So, okay. Okay, so here's a lemma. Trying to remember if we're going to do this later or not. All right, the claim is if I look at two different points in the log, the corresponding witness trees will be different. Okay, why? So if the roots are different, then they're definitely different. And if the roots are the same, yeah, so let's say I have a witness tree over the first 5 events and a witness tree over the first 10 events. Then at some level, so the witness tree over the first 5 events is using some subset of these events, right? Maybe 4 of them or something. And they're all definitely appearing also in the 10th one because of the same roots. Right? So that means, okay, there's 4 of them here. There's at least 4 of them in the first 10, plus the root itself. So they're just strictly bigger if they have the same roots. So it might not appear as a subtree because as I build down, I'm going to put in the smaller, but it will be a subset of kind of events. So if I look at the first 5, right, and I have a witness tree for the first 5 events, and then the question is the 4th event in the tree? Well, that depends on if it depends on event 5. Is a 3rd event in the tree? That depends if it depends on the first 2, and so forth, right? So for the 10th one, if event 5 and event 10 were the same event, so they have the same root, then I know that the same ones that are dependent, that follow the chain of dependencies from event 5 will also, at the very least, qualify for this tree. So that'll give you that subset plus the new 10th event. Yeah. That might be even more. That could be the same. Yeah, so, yeah, but then if you count multiplicity, so if events are repeating, then they're just gonna, but the total number of nodes, so there may be several nodes with the same event labeled on them. It'll just get bigger and bigger. Yeah. Okay, so, so if that's the case, if I know that in any log, all of the witness trees are different, okay, then this last summation can be turned into this claim. I'm going to sum over all the witness trees that are labeled with AI, say, what is the probability that this witness tree appears in the log? Okay. So, it seems crazy, but look at where we started and ended. The first question is quite reasonable. What is the expected number of times I relabel or resample event I, or resample clause I in your SAT formula? And at the end, we have this crazy thing of like, well, of all possible witness trees that start with this particular clause at the root, what are the odds it appears anywhere in the log? So something magically has happened, and we're going to focus on this second question from now on. But I just, as we get into the depths of this question, I just want to remind us we started at a sane, reasonable place. Yeah. This individual one or the sum? So TJ is the witness tree on the J after J events. And T is some particular witness tree. There's, infinitely many possible witness trees out there. Like any arrangement events, yeah. Yeah, no, WI, yeah, exactly. So WI just referring to the whole family of possible witness trees, just as kind of combinatorial objects, trees with nodes labeled by events that could have somehow come from this kind of thing. With root I, yeah, this proof is a little bit more. Oh, we're already out of time. So this proof is a little bit more involved than the past ones. So we'll have lots of things going on the right hand side to try to remind us of the parts. So let me just tell you then what we're going to try to do next, so that you're super excited to come back Wednesday. Um, thought there's something here. Okay, so we are going to look at this. What is the probability for fixed t that it appears in the log anywhere for any j? And yeah, and I guess we're going to try to show this. So this is the lemma we're going to try to show, and this will be actually the biggest leap, I think. Okay, the probability that a particular witness tree is generated from your log is bounded above by taking all those events, over all the labels in your tree with multiplicity and multiplying the probabilities together. Okay. Okay, so that's where we'll start next time. I know this is much more involved than usual, but so be it. It's in proportion to the result we're proving. So this is what we'll do next time. All right, thank you. We'll try to finish off our discussion on the Lovász local lemma today. Again, this is always like one of the toughest proofs of the year, so we'll see if we survive. Um, it'll be a proof that I would be very happy if we can clean it up in any way, but that's okay. So just to remind us, one motivation is, K-SAT problem. We've seen that a few times before. And, as a warm-up, if I told you that you had a K-SAT formula and you had less than 2 to the K clauses, then the union bound already tells you that the F is satisfiable. So random assignment by the union bound. So there are some kind of silly, trivial cases. Now, consider this algorithm, which almost seems like a natural heuristic. So you first randomly sample all your variables, okay? And now, every time you find an unsatisfied clause, so some clause that's unhappy, you just resample all the underlying variables, okay? And you just keep going until the formula is satisfied. If you win, you win. If you don't, you don't. Okay? But that's the simple algorithm. And the amazing claim that we're going to try to finish the proof of today is this. If every so it's about locality. So if every clause intersects, let's say each clause intersects another clause, if they share an underlying variable, that means it can be xi and xi naught over here, just underlying variable, right? So it's saying that if the number of the kind of the degree, so to speak, of that sort of auxiliary graph is at most 2 to the k over e minus 1, then this algorithm will terminate and it will be satisfiable, right? So if somehow, like, if you sort of had thought about your formula as a graph where the clauses are nodes, and if the degree is small relative to 2 to the k, then the formula is automatically satisfiable, right? Which is a spectacular claim. Not only that, but you can find the satisfying assignment. So one way to interpret 2 to the k minus 1 is that, well, definitely d has to be less than 2 to the k because that's enough to sort of take a union bound over just a neighborhood, right? And sort of what's going on is like, okay, I have a clause and first a random, we already know that a random assignment is going to satisfy most of the clauses, right? We did that like the first day of class. Now I go to a clause and I resample everything, and that might mess up some other clauses nearby. It'll almost definitely fix this clause. And so the infections will grow as you resample things. But if there's not that many neighbors, the sampling in general is good. A random sample will satisfy most clauses, but still some mistakes will leak out and stuff like this. And so you're hoping that if it's locally kind of simple enough, sparse enough, then maybe the randomness can sort of outrun the spread of mistakes at some level. Okay, question. Yeah, sure. So if I resample C1, then C3 is unaffected. But when I sample C2, now C3 is sort of suspect. I need to at least double check I'm still correct on C3. Yeah. So in general, the mistakes can propagate. And so if sort of you have lots of interactions, then it's going to propagate really fast. But here it's saying, okay, the degree is at least bounded, right? So when I sample C1, there's only so many choices of C2, a relatively modest number of C2s it can infect. And if I do mistake on a C2, then it might mess up some C3 and so forth. Yes. Yeah. No, it's saying there is a satisfying assignment. It'll randomly find one. Yeah, it doesn't really say anything about the plurality, and I don't know if anyone's asked that question. Yeah. Yeah. That's an interesting question. Yeah. Yeah. That's what we'll show. And we'll show actually very precisely that each clause, what does this mean? Oh, okay. I thought you were doing this for show. Um, okay. Uh, so each clause will be sampled 1 over d times an expectation, which is actually less than 1, right? That means over m clauses, you'll sample about m over d in expectation. Yeah. Oh, I guess an expectation polynomial. Yeah. Which is okay. Yeah, for us. We don't mind that. So that's the claim again. And the history is that the existence of a satisfying solution has been known since the 1970s. Okay, there's this famous thing, probabilistic method, if you're in this kind of discrete math space. And it's the algorithm that was only, I guess, 15 years old. Okay, so it's almost old enough to have a driver's license. But this was done by a graduate student and was a complete shock. So this was sort of like, there's a few questions out there that are just like really obvious, and often these math things, okay, we know there exists something, but we don't have an algorithm for it. This is like really ripe for a computer scientist. but it had stumped us for many years because the existence is a very famous result, and you can use it for other settings. I'll remind us the more abstract setting we're going to do this in. I feel like we're going to spend half the class just recapping, but that's okay. So a more abstract version, which you can use all over combinatorics, is this. So you have n events that you're trying to avoid. So for SAT, one event is a bad clause, right? And I want to avoid all of these bad events. Okay. So in graph coloring, I might be assigning colors to the vertices. A bad event is an edge where both endpoints have the same color. And I want to avoid all of the events. So the question is there some way to guarantee that is it possible for none of the events to occur? And of course, if they're independent, the answer is yes. And without any assumptions, the answer is no. Okay. So, so there's sort of, this is the math theorem from 1975. It started in a more modest form, I think, and became more general. So I'm writing AJ tilde AI whenever I have two events that depend on each other or aren't independent. So in the case of SAT, they share a variable. Okay, so we're assuming the dependencies are sparse. And so technically, if you're able to assign values, if there exists any values to the A's, so you come up with these XAIs such that this always holds true. The probability of AI is at most XAI times taking the product over all the neighboring events, 1 minus the event, then it's possible for none of the events to occur. That seems very technical, and it'll come up in our proof. Okay, so it just says if there exists some X. Now, so for example, in a more uniform setting, if every AI depends on at most D other events, so if it was like a graph, then the degree is D. And you knew that EP plus 1 is at most 1, then yeah. And that would just come from plugging in 1 over D plus 1 for all of the X's. Anything you want, yeah. So there are more sophisticated situations where, you don't have this uniform. In non-uniform settings, you will maybe want to make the X's depend on the degree of each vertex or each event and things like this, yeah. So there's so these are sufficient conditions for none of the bad events to occur. Okay, and then there's like a lot of spectacular combinatorial examples where this proves that something exists that you would be surprised by if you were interested in the area. So okay, right. So this more general event version can also be turned into an algorithm. That's the one we formally analyze, although I'll keep using SAT as a running example. But to turn this into an algorithm, we have to make it a little bit more concrete, because what does it mean to sample an event? So we're going to assume that there's some underlying set of variables denoted by the x's, okay? And that the events are a function of the variables. So for SAT, the variables will be your n Boolean variables. And then, whether a clause is satisfied is a function of those k variables in the clause, right? And so each event is determined by some subset, and we'll say that they're adjacent or kind of connected to each other only if they intersect. Yeah. Yeah, you can assume it's finite. What happens if it's not finite? I don't know. It's a little ambiguous, but I'm sure it's okay if you're very careful about it. Yeah, here it'll be finite. And you can assume V, that means V is also finite. Yeah. Okay. Okay, so the more general version of the algorithm then is that you first sample all the variables, and while there's some event AI that occurred, it's a bad event, so you don't want it to occur, you'll resample all the underlying variables. Okay, so it's just generalizing SAT. SAT, the bad events were bad clauses, and you sampled the underlying variables. Now this is some other bad event. Okay. All right, and that's the form in which we'll analyze it. And I guess, yeah, if you come up with these values, the first part is the mathematical existence theorem. But the algorithm will also show actually samples a particular clause at most this many times. Okay, it's hard to interpret this. This is just what's gonna come out from the analysis at the end, and then gives you reasonable bounds for SAT or whatever once you plug in the right value of x. Okay, so that's the theorem, and now we got to get through the setup. So this is easily the most, I think, delicate proof we've done so far. Maybe will be the whole semester. So we're going to introduce two things. One's called a log and one's called a witness tree, where a witness tree is really bizarre. A log is pretty simple. I'm just going to list the events as the algorithm samples it. So maybe the first iteration is samples event 1, so I write A1. Then samples event 7, I write A7, A11. A1 can appear again, right? You might resample the same event. That can easily happen. And we want to bound the expected length of the log, right? And that's quite tricky. It's not clear at all how to approach this, right? So maybe just to remind us, our algorithm is bizarre. It's not like always making progress, right? Oh, I fixed this clause. I made more mistakes. It seems like I'm worse off than before, right? So, yeah, what we're going to do is very indirect, but I don't see an easy way to prove this. This algorithm is quite bizarre. Okay, now the other object is a witness tree. A witness tree, for the starting definition, it's a tree where the nodes are labeled by events. Okay, so when I refer to that'll be the definition, but we're going to construct them in a specific way. So that's the same thing. Okay, so let me remind us our process. So what we're going to do is we're going to look at our log and we're going to look at prefixes. So say the first 10 events. And then we're going to follow this bizarre procedure to construct a quote-unquote witness tree out of it. So what you do is you start with that last event, A10. And that'll be your root. Okay. Then you go to that 9th event in your log. I'll just call it A9. Okay. And you check to see if it's dependent on your root or not. Okay. If it shares any variable. If not, you're going to throw it out. If it is, you'll make it a child. And then you go to A8. And you'll say, okay, is this 8th event, is it related to any of the events in my tree right now? If it is, I'll make it a child of the deepest part of the tree. If it's not, I'll throw it out. So not all things in the log are going to go into the tree. It's just things that are kind of like, can trace back to that 10th event, which is the last event in your prefix. Then you put it under A10. And if it was related to A9 and A10, you would put it under A9. The deepest, yeah. So this was the example we did together. So a log of 6. So this became the root. This one we put underneath. This one we put under here because it wasn't related. This is for like SAT. This one here, x7, x8, x9, doesn't have any relationship to any of these. So we left it out. This one went here. That one went there. Okay. It's a bizarre, yeah. Huh? So we look at a particular prefix of the log, and then the root is the last event in the prefix. So here this is a prefix of 6 events, the first 6 events in the log. So we start with the 6th one. But every prefix will generate a witness tree, and they may look completely different, right? Because for starters, the root is already different, and that sets off a different chain kind of reaction. Right? But at some level, it's kind of like, what's sort of going on is like, okay, somewhere under here, there were some variables that made this unhappy, right? Which is why I had to resample it. And we're going to kind of trace back like, okay, so that could have come from variables from here, from here, from here, from here, right? This is at some level trying to map out like, where are the variables coming from? Okay, because another event like x7, x8, x9, has really nothing to do with any of the variables that lead to x1, x2 naught, x4. So we kind of can leave it out. And the rest is sort of saying, okay, yeah, you had to do sample this before you sampled this, things like this. We'll make it more precise in a moment, but it's sort of mapping this out. Okay. And it's a weird object. It's not super easy to interpret. It's really something to make the proof work. Okay. And it's a very creative proof. Okay. Um, so two observations. So let's say I have some witness tree for like the first 10 events or something. And let's say that I'm looking at the fourth event and the seventh event, and they're related to each other. I know that if the seventh event was in the tree, then the fourth event is going to be in the tree. It's going to be lower. At the very least, it'll be the child of the seventh one, or it could be even lower. Okay. Another observation is that, so as you go through the log, you have each prefix generates a different tree. Tree for the first four, tree for the first five, tree for the first six. And you can see that they all have to be different. The reason is that if I had two trees, one for this prefix, one for this bigger prefix, and they were the same, well, for starters, they have the same root, right? And then everything in the smaller tree, for the smaller prefix, they're all going to have some like dependencies going back to here, right? So all of these that appeared in this smaller tree are also going to appear in the bigger tree because it'll be connected to the top one, including that one. Plus you have one more, yeah. So you'll be at least one node bigger if the roots were the same. Okay, so also all the trees will be distinct. And, right? So I'll go straight to here. Okay, so suppose I'm focusing on the question of I have a particular event AI. How many times is AI resampled? Well, if I look at the log and I look at the corresponding witness trees, it'll be exactly how many of the witness trees have AI at the root. Okay, so that's there, and so I can sum from all the possible indices in the log 1, 2, 3, 4, 5, and I sum over all the trees with root AI. That's what WI refers to. The witness trees with root AI. So what's the probability that the jth tree, the tree for the first j entries, is equal to this particular tree with root AI? Okay, but because all the different indices have different trees, I can simplify that a little bit to say, summing over all possible trees with root AI, what are the odds that it appears anywhere in the log? Because it can't appear twice. The same tree can't appear twice. Okay. Again, it's pretty crazy. Okay, so now what we're going to try to analyze is we're going to fix a particular tree and just try to figure out what are the odds it shows up in the log, or what are the odds that the log generates this tree anywhere. Yeah. TJ is the tree after J entries in the log. So the prefix of the first 20 entries will generate T sub 20, some witness tree for the first 20 events. TJ is from the log and T is inside the sum. So it's some particular witness tree with root AI. Yes, except we're just focusing on the ones with the root is for AI. Yeah. Yes. Yeah. That's right. That's right. Exactly. Some of these trees may be impossible given the problem structure, and they'll just be zero or something. That'll be okay. Yeah. Okay, yeah, there's n events or m events or something, and yeah, the trees will be labeled by those n events, and things in the news, and things my mom tells me over the phone, and all these other things are not part of the witness trees. Yeah. Okay. Yeah, I feel like that could be said of many things. Okay. All right. So here's the exact claim. So if that witness tree is labeled by events, those events have some probability of occurring. And remember, an event can show up on multiple nodes in a tree. And so I'll say P of t is multiplying the probabilities of all these events as if they were independent. Okay. The claim is that the probability that this tree with a particular set of labels appears in the log is at most multiplying all those individual events together. Because they have to happen in a specific order. Um, I feel like that intuition's going to play in, but I wish it were that simple. Yeah, we do. So somewhere we're going to have to take into consideration there's some dependencies among the events, right? And the claim seems simple, but there's something. I mean, there is a long column on the right of notes already, right? So I don't even know if it's legible, but okay. So how are we going to do this? Hopefully I left us. Okay, good. I did leave us something. All right. So again, don't ask me where these ideas come from. I'm just a messenger. So what we're going to do is we're going to introduce a checking. So we're going to try to couple the processes. Um, so we're going to define this checking procedure, which is basically, in one of these trees, the events closer to the bottom are coming earlier in the log in general. Okay, two adjacent siblings is a little bit ambiguous, but if something's deeper than another, then it came earlier in the log. The log, yeah, if you're reading off the entries from the log in the tree, the entries that appeared into tree, because some were left out, it'll be going bottom up. And what we're going to do in check T is we're going to look at the events bottom up and sample them, sample them, sample them, and see if they always occur. Okay, so okay, so for every event A, I, J, and T, in decreasing depth. So decreasing depth is confusing, but the biggest depth is the bottom. So decreasing depth is actually going up. Yeah, it's like crazy. You write your own notes and you still confuse yourself. Okay, you're going to sample the underlying variables. If the sample does not induce the event, then you say it fails. Okay. Now in the log, the event actually occurred, or in some sense occurred, because that's why we had to resample that event. But there's some reassignment of. Is there nothing else? Otherwise, you return. Yeah. When you erase, if you erase the underlying, if you hit the underlying letter on top of the white square, then anyway. Yeah. This apparently this is like life before PowerPoint existed. Yeah. Yeah. So my tree will look like an arrangement of clauses. Um, and I'll start with the bottom ones and gradually work my way up. And I'll sample the variables. And if the clause is not satisfied, that means the event occurred, the bad event occurred. So I keep going. If at any point one of those clauses becomes satisfied, which means the event didn't occur, then the check fails. Okay. So given a tree T, what is the probability that you pass the check? Hmm? You just multiply the events together, right? So that bottom clause, there's some odds of it failing, odds of it failing, odds of it failing. So you just multiply it together. So P of T up at the top is the probability that check T passes. all the events occurred as if when you sample them kind of independently. Okay. So that's sort of one side of this. Okay. Okay. Good. So now, oh man. Okay. So what we want to show then is that the probability that this tree occurs in our log, which can be written out as tj equals t for some j, okay, is bounded above by the probability that check t succeeds, which of course is on one hand just those probabilities, but somehow we'll look at sort of the semantics of check t and be able to sort of pair them up for a fixed set of underlying variables, and then you can see that, yeah. So we're going to kind of couple the underlying variables to prove this, which I don't think it's a style of argument we've done before. Okay, so good, good. Any questions? Questions are highly appropriate. Yeah, so that's what the claim is. The claim is that there's some connection between these two. So yeah, we haven't introduced that yet. So that's exactly the gap we're trying to get. And in general, you know, TJ, right, and the log is some kind of complex process where there's all these dependencies on top of each other, right? It's very complicated. It's hard to think about. And check T is sort of very simple because all these events are treated independently and just sample, sample, sample. And that's reflected in the probability, which is just a product of event probabilities, right? Which is obviously simple and it's equal. So it is true. This is this complex organic monster. And this is a relatively simple thing. And now we're going to try to relate the two. Yeah. So you've pinpointed exactly the issue. But the claim is okay? Okay. So, okay. All right, here's where things get hairy. Okay. Okay. So, what we're going to do is we're going to imagine, so the algorithm is going to use many samples of the variables, right? Now imagine you had generated all the samples ahead of time, and don't even worry too much about whether you can generate infinite amount of stuff ahead of time, okay? And then you just then you look up the table, right? So basically you generate your whole random bit string at the beginning for each variable. And then when you say, okay, I want a new copy of this variable, then you say, well, I've already had 5, so give me entry 6. Okay, so what we're going to do is we're going to generate a table ahead of time. Okay, and then we're going to try to have the algorithm and our check procedure use the same underlying variables in a certain way. And we're going to kind of couple the processes together. Okay, so in other words, in both cases, the whole thing is driven by a bunch of outcomes for those underlying random variables. We're going to fix one outcome of the infinite range of, including the repetitions, repeated samples. We're going to fix one particular outcome, and then show that on this outcome, if t appears in the log, using those variables or something, then check t will also pass using the same variables. Okay, so that means every kind of every driving set of variable outcomes under the surface that produces the thing in the log will also map to checking t, and then that'll give you the inequality you're looking for. Okay, so I don't think we've done an argument like this before. This is called coupling. Okay. All right. Okay, so you fix these ahead of time, and we're going to run, using the same samples, and try to show that if the log induces t, then check T succeeds. Okay. Good. And that'll give us our less than equal. All right. So I was probably supposed to erase some of this so it's more fun, but that's okay. Now let's look at my log, which is going through some events. For some reason, instead of writing A1, A2, A3, I wrote A sub I sub 1, A sub I sub 2, A sub I sub 3. Forgive me. And now, when the first event shows up in the log, AI sub 1, then I know that the underlying variables were bad and generated the event, right? And so I can kind of say, okay, uh, let's take stat. Then you actually know the exact values of the underlying variables even, right? So I'm going to say, okay, sort of this event in the log used the first sample for all of those variables, right? Now, the second event in the log also used samples for some underlying variables. If they're completely different than event one, then they're using the first samples for all of those variables. But if they share some events with the first event, then those variables you'll be using the second sample. Okay. So in this table, it might be like maybe that's big. These events, these variables were used by were the ones resampled for event one. Okay, like the first, second, and fourth variable or something. And the second event used these samples, 1, 2, and then maybe another one down here or something. Okay, so I can read off sort of, which of the samples from the table led to this event. Okay, and that must have been the case. Now, now, okay, so whenever, so what really matters is like, T is going to be, when I check T, I process the events in some particular order and I read off the particular variables from the table. And likewise, the variable drives the log, and the log is sort of looking backwards at what samples generated this event, right? And so I can associate, certain squares of the table to events in the log, and also certain squares in the table with the events being used to check the events in the tree. You want to make sure is that the squares are matching. Okay, so let's like take the first variable, right? Variable x1 or something. So yeah, so if you just kind of think about it, because the t is always doing this lowest child kind of thing. So whenever you share variables, it'll be lower. So whenever like so in the log you can look at like, oh, here are the first 5 events that use variable 1. They're going to appear in the tree in the same order because they'll at least be children of each other as you go back. Okay, and then you will find, I don't know if I wrote it out in enough detail in the notes, that they do correspond perfectly. So yeah, let's see if this is convincing or not. So okay, so I'm looking at a particular node in the tree corresponding to a particular entry. Okay, now for every underlying, my J's and I's are kind of mixed up. Let me fix this. So if I look at a node in a tree with label AI that's being checked, and I look at some particular variable, then now the entry in the log is going to be using the H copy of this variable if it's the H event in the log that uses that event. Okay? And then if you look at the tree, all of those entries, did I not write anything else? Well, okay. So we'll just make it up. So if you look at the tree, though, all of these h minus one other events are going to appear under uh, this node because at the very least they overlap over this vertex. So all h minus one events will be checked by the check procedure first and use up the exact same samples. It'll use up the first hi minus 1, just like how the event in the log use up the first hi minus 1. So they'll both use checking this node in the tree and what I associate to the event in the log will use the same copy of this jth variable. And that applies to all variables. Okay. Yeah, exactly. That's a perfect point. So meanwhile, we know the event occurred in the log. So the underlying variables made the event happen. So when we check the tree and we're checking that node, I'm using the exact same copies of the samples in the table as made the event occur in the log. So it will also pass the check for the tree. The event will occur when you're checking the tree. Right? Yeah, so that's the argument. It kind of makes sense. Okay. Yeah. Yeah, that's what learning's about. Okay. In the log. Yeah, but the advantage though is that in the tree checking, so we couple it. So the complicated thing is the event log and how it's generated because that's something. So we couple it so that we can say, oh, if the event log happens, then the tree also would occur in the log. So we couple it like that, exactly as you described. But now the win comes from the fact that if I wasn't worried about coupling and I'm just analyzing the tree check, I know exactly that probability, right? Just multiplying the events together because the order is predetermined and there's nothing dynamic about it. Just do one event at a time. It's very easy. And but then the coupling lets you take the complex thing and kind of map it into good instances of the tree thing. But then the overall tree thing, just overall randomness is easy. Yeah, yeah, yeah. Um, what's this matter? Okay. Oh, I see. I did write out the details. Okay. Um, good. So we reached this point now. Yeah. So what we showed in this coupling argument is the probability of a particular tree occurring is at most just multiplying all the probabilities of events together. Yeah. Okay, good. We're making progress. We're not done yet. So now the claim, huh? Oh, as opposed to lemmas? Well, we proved the claims. I'm not like a politician or something. Uh, uh, I don't know. Yeah, I think it's called a lemma in the notes. Uh, oh, what would you call it? Okay, they're back. The Galton Watson trees are back. So what I'm going to do is I'm going to imagine a process where um, I first generate. Oh yeah, we've been upgraded. Okay. We start with the root AI. That's just a fixed part of the tree. And now for every possible event that's adjacent to it, like connected or dependent on it, I'm going to generate that child with probability xaj. So the x's are going to come into play and they're going to make more sense in hindsight. Okay? Because they're not exactly the probabilities of the event in the original statement of the problem, right? So, so this will occur with probability aj will occur with probability xaj. And if I don't have an edge to some ak, that will occur with probability 1 minus xak. Okay. And what we're going to do is we are going to fix a tree, analyze the probability of this tree being generated. We'll get something nice. And then at the end, we're going to use the fact that this random process generates only one tree. So all of these QTs can only add up to one. Okay. So good. Okay. So you have some tree, right? And so it's going to be like AI and then, some AJ and AK and stuff like this. And then you're going to get more children, more children, more children with various probabilities. Okay. And of course, there are some children that are missing, right? These are the children that died. Okay. They didn't get sampled. So if this is the node N, then I'm going to call this set BN, which stands for BN, maybe bad N. I don't know. Okay. So those are the things that aren't in the tree. Okay. And then for a node, I'll write A sub n to be the label that the event that's labeled on the node. Okay, so I'm sure the notation is confusing, but that's how I like to keep it. Okay. Uh, all right. So, okay, so now what is the probability of a particular tree occurring? Okay. So for every node in the tree, okay, the probability of that node as a child being spawned at that point in time was xn. Okay. With only one exception, which is that the root was already automatically in it. So I need to divide by the root, which a little bit confusing is 1 over AI. So we're looking at particular I. Okay. And, but meanwhile, it is x of AI. And it's not x of n, it's x of an. Okay, good. Yeah, error correcting codes. Okay. But that's not all the probability, right? Because not only do we have the probabilities of the children that survived, but we also need to account for the probability of the things that were omitted. So there is a sort of really a parentheses in here, and I'll take the product of all events AK that were omitted in Bn 1 minus x AK, something like this. Okay. Yeah. Oh, so this is not necessary, but it is nested because we're doing a product over n for a particular node in the tree. So each node in the tree has all the children that it didn't have, and that's what this represents. So just making like extra obvious that this n is actually generated by this product. Yeah, there's a lot of notation going on. Um, okay, so now what we're going to do is, okay, so now what I can write is this. So I'm going to sort of expand this out to all of the nodes adjacent to anything. So we're going to write, so first the first part stays the same, 1 over x ai. I'll write it out first, n and t. And what I'm going to do is I'm going to put in a 1 minus xan here. So this green product was only leaving out the things that did get sampled. So now instead of just doing over all the ones that didn't appear, I can do all AK that are incident to this event on node n. Oops. 1 minus x a k. Yeah. So this is saying for every node, look at every neighboring event and the odds of it not happening. Okay. And then this is saying for every node, look at all the events that are neighboring but didn't happen and then the odds of it not happening. So I'm adding in the 1 minus xa ak terms for something that really did spawn as a child of an. So ak was an event incident to an, so it could have been a child, and it did become a child. Okay, so that's actually, so I've added some terms here, but it's canceled out because I added this back in. Yes. So if you compare this to this, okay, so Bn is expanding to include the things that were sampled, okay? And to account for that, I have this 1 minus term for the actual node in the tree. So it'll cancel out. We're really close. I know we're out of time. Now, let me just simplify this. Um, uh, and I should add that the only event in the node in the tree where you don't add another one is the root, because the root was never going to be a child of anyone. So you add this one back in because you had thrown in an extra one here. Well, it better be true because we're 1 minute over. Let me let me just keep going, and we're almost there. So this is 1 minus x ai divided by x ai, uh, the product over all nodes in the tree. Why did I write this? Um, uh, okay, so I think maybe this is okay. Okay, now, oh, sorry, I'm rushing. So this term here is P of t. Okay, so Uh, P of t is at most, okay, there might be some typos. Let me just finish and then I will recover tomorrow. Uh, the product of an, and this is our assumption is that we have some, this is our, if you remember, we had this condition about x satisfying certain things. One minus x aj, which is supposed to be, I'm a little worried about some terms not working out, but I'll figure that out later. 1 minus x ai q t. Okay, now what? So now if you sum over all t, the sum over all t is less than equal, p of t is less than equal to x ai over 1 minus x ai. The sum over all witness trees was labeled I. That should be a W, QT, and that's at most 1, and that is the end. Okay, so let me double check with the notes, but that's how it all adds up together. Okay, and ultimately what we've shown then is, this is the probability of any tree, witness tree with root AI appearing in the log. Right, because PT is just one of those trees. The sum of PTs is any of those trees. And it's at most, you put it all together, xai over 1 minus xai. We rushed the calculations a little at the end, but that can be verified, just line by line in a proof by just working through the Watson tree and doing some manipulation. Okay, so somehow this xai over 1 minus xi comes out of that calculation. All right, I'll end it there. Great job, guys. And we'll do something else Friday. Okay.